All right, let's learn about acid-base neutralization. And so what you already know about acids and bases is that when they combine, they go through a reaction. And what we've learned so far is that when an acid combines with a base, as long as we're talking about Arrhenius acids and bases, what gets produced is salt of some kind and water. And the salt we're most familiar with is sodium chloride, and that salt is indeed produced in a reaction that looks like this. And so here's a neutralization reaction between hydrochloric acid, which we're pretty familiar with, at least the name of anyway, and this compound called sodium hydroxide. And what they create over here is sodium chloride and HOH. This is hydrogen hydroxide. And that is equivalent of water, right? There's your two H's, H2, and then an O. That is a water molecule for all intents and purposes, okay? So I've made these little colored balls here to kind of represent the ions that are present. So the red is the hydrogen, blue is the chloride, yellow is the sodium, green is the hydroxide. And you can see that in a double replacement reaction, the hydrogen and the sodium are going to trade partners. And so the red ball that is here is now connected to the green ball over here. So we're just replacing the ions. Remember how that works. Okay, so when the thing about these ionic compounds that are interesting here, the acid and the base, which are ionic, is that when you put them in water, what happens is that they will dissociate, and we've talked about dissociation before. So just picture that this is a vessel of water into which we've placed some hydrochloric acid. And what happens is the red and the blue balls separate from each other in a dissociation process, right? So we've got the ions that are just sort of floating around, unconnected to each other. And then the same thing is happening with the sodium hydroxide. The sodium ions and the hydroxide ions are separate from each other. But now imagine that you pour those two solutions together, and then we can allow the ions that want to pair up to actually pair up. And so that is represented by this arrow here. And what we see on the other side of the reaction is the sodium chloride, which is the yellow and the blue connected to each other, and the hydrogen and the hydroxide connected to each other as water. And so really what this is salty water. And the salt that you're familiar with here, the sodium chloride, that is just due to the ions that are involved in the reaction. So not every salt that gets produced is going to be sodium chloride. There's lots of other chemical formulas that represent what we call a salt that is not something that you're think of typically as salt. So let's write out a couple of neutralization reactions here and see what this looks like. So here we have zinc 2 hydroxide and hydrochloric acid. Now you might be wondering at this point, like, why the names of the acids are kind of funny. Hydrochloric, and it's got to do with the hydrogen and what it's bonded to, and here's some names and formulas. We have some that are just known as just binary acids, and they have their own naming system where basically the hydrogen we call hydro, and then the ion that's connected to it usually comes from the halogen group, and they combine in a 1-to-1 ratio. And that's why we call it a binary acid, because there's just two ions involved here. And they kind of just have their own naming system. These other guys here, like nitric acid, phosphoric acid, sulfuric acid, and carbonic acid, these are what we call oxyacids. And they're a hydrogen ion, or two or three sometimes, connected to a polyatomic ion. And they just, they have different ways of naming, but you'll see the formulas and you'll see the names, and just, maybe put this list of acid names and formula in your notebook, and then you have reference for these things. The bases don't have a naming system, but the acids do. Okay, so anyway, there's that. We'll refer back to this here in a few minutes. So zinc hydroxide combining with hydrochloric acid. So the formula for zinc 2-hydroxide is Zn combined with a OH. And you'll notice here I've got the base listed before the acid. That's fine. Even though typically, when I explain it, I always put the acid first, but it doesn't matter which one goes first. So because this is a +2 oxidation number on the zinc and the hydroxide is a -1 oxidation number, we need to subscript the hydroxide with a 2. And then we're going to combine that with hydrochloric acid, and we can refer back to our list of names and formulas. That is just HCl. And in these neutralization reactions, remember they're double replacement. So we are going to make 2 new compounds. And just think about how this goes. Remember that the positive zinc and the positive hydrogen ions are going to trade partners. And so what we end up getting is zinc hooking up with the chlorine. And zinc still has its +2 oxidation state, so we have to subscript the chlorine with a 2. And then the other thing we make here is hydrogen hooked up with the hydroxide, HOH. And that's a water molecule, H2O, right? So where is the salt in this? It's this one, zinc chloride. That is not a salt that you would want to sprinkle on your food necessarily, but technically this is salt because it's the result of an acid-base neutralization reaction. Okay, and so with everything, it's always mandatory that you balance the chemical equation because we can't have 2 chloride ions on this side and only 1 over here. We can't have 2 hydroxides on one side and only 1 over here. So typically these balance out pretty easily. So we're going to use our coefficient numbers to put a 2 here. Now we have 2 hydrogens, 2 chlorides, 2 we can put a 2 here. Now we have 2 hydrogens, 2 chlorides, 1 zinc, and 2 hydroxides. So this is a balanced chemical equation, okay, for the neutralization of these acid and base. Let's do another one. Sulfuric acid and aluminum hydroxide. So we'll go to our list here and look for the sulfuric acid formula. There it is, H2SO4. So let's write these formulas here, H2SO4, and we're going to react that with aluminum hydroxide. So that's aluminum and hydroxide, OH. Now remember that aluminum is in the +3 category on the periodic table. It's got a +3 oxidation state compared to hydroxide's -1, which means we subscript the hydroxide with a 3. Okay, and now in a double replacement reaction, what we're going to make, I usually put the salt first, aluminum sulfate, Al2SO4 3. And remember where these little subscripts are coming from. The 2 is representing the -2 oxidation state of the sulfate, and the 3 is representing the +3 oxidation state of the aluminum. And then, of course, the other thing we make is a combination of the H and the OH. There we go. So there is our unbalanced chemical equation. And so we need to make sure that we get this thing balanced out. So we'll just sort of do this quickly. 2 hydrogens. Actually, we've got 3s and 2s. So let's see. We need to do 2 aluminums. That's 6 hydroxides, which means we're going to have to put a coefficient 6 over here. 6 hydroxides, 6 hydrogens. There's our 6 hydrogens and our 3 sulfates. There we go. This is a balanced equation now, okay? So that's how you would write the neutralization reactions if you've been given the names of the acid and the base. And again, just take note of the acid names and formulas so you can tell what formula to use in your equation, okay? Now, the other part of this process that's kind of fun, I think, is identifying the parent acid and the parent base. So these are when I say the parent, I just mean that, like, if this is the base and this is the acid that join together to make this salt, we call these the parent acid and base, okay? So if you only know the formula of the salt that is created in a neutralization reaction, you can work backwards to determine what the parent acid and the parent base are. So, for example, if you are told that calcium phosphate is made in a neutralization reaction, you can kind of work backwards and understand what the base and the acid are that made that salt. And so let's just put our reaction arrow here. And if this is the salt, remember it's a product, so it goes over here, Ca3PO4 2. And this, remember, these subscripts are resulting from the +2 oxidation of the calcium and the -3 oxidation of the phosphate. The other thing that is, of course, always made is HOH. And the reason that I don't write this as H2O in these equations is because when it comes down to balancing the chemical equation, it's easier to balance if it's in its kind of ionic form like this. Okay. Also, when you work backwards, it's kind of easier to see that we're working with 4 separate ions, and then you can kind of backtrack to see how these are going to be created. So remember that the salt is always made from an acid and a base, and we know that an acid is always going to start with hydrogen and then have some ion behind it, and the base is always going to start with something and have a hydroxide ion behind it. Right? So this is the general formula of those Arrhenius acids and bases. So now let's just kind of backtrack. So here's the hydrogen, and here is the hydroxide, right? So this hydrogen hydroxide stuff, that's the hydrogen and the hydroxide that came from the acid and the base. The salt is the anion that is part of the acid and the cation that's part of the base. So let's just put these in place. So remember that calcium is the positive and phosphate is the negative. And so positive is going to remain positive. That means calcium is going to hook up here with the hydroxide, and the phosphate ion is going to be part of the acid. Right? There we go. And so now we just need to formulate these acids and bases correctly by referencing their oxidation states and making sure that we have the formulas written right. So phosphate has an oxidation state of -3. That means that we have to subscript the 3 on the hydrogen. And hydrogen is a +1, so we don't need any additional subscripting. Calcium is +2, hydroxide is -1. That means we need to subscript our hydroxide with a 2. Okay, and of course, we would want to go ahead and balance this equation just to finish it off, but we'll do that in the next example. Okay, here is the next salt that gets made in a reaction. So let's just kind of do this the same way we did the last one. So here we have ammonium bromide, which is the salt that is created in this neutralization reaction. So let's just do the same thing we did. We're going to put that formula here. Okay, there are no subscripting requirements here because ammonium is a +1 polyatomic ion and bromine is a -1 ion as well. So 1-to-1, no subscripting. And then the other thing we make, HOH. Okay, so let's backtrack to see what the acid and base are that make this. So remember that the hydrogen and the hydroxide, these are the ions that are part of the acid and the base. So we have our acid, which starts with hydrogen, and then we're going to have a base which ends with hydroxide. Right? And so let's just put these things in their appropriate places. The positive ammonium must go here. So the base is ammonium hydroxide, and the the bromine here then goes right here behind the hydrogen. And so this is hydrobromic acid combining with ammonium hydroxide, and those are the apparent acid and base, and they join together to make that salt. Okay, let's balance this one just for fun. So one hydrogen, one hydrogen. Actually, this one's going to balance all out because all of the oxidation numbers are ones. So that makes life very easy in terms of balancing. So anyway, I hope that helps with these neutralization reaction problems that you'll be doing. And all right, that's it.